Hello, I'm Henderson, a PhD student in astronomy at The Ohio State University. Today I'll be telling you about my recent paper, titled Candidate Gravitational Microlensing Events for Future Direct Lens Imaging, on which I worked with Dr. Chung-Go Han at Chungbuk National University, and also with a large team of collaborators. Gravitational microlensing occurs when the light from a background star is lensed by the gravitational field of a foreground star. The arising magnification of the background source, shown here, provides a tool with which it is possible to search for planets around stars that are faint and/or distant. However, it is generally difficult to measure the physical parameters of the lens system. The fundamental constraint is not that the lens is detrimentally faint, but that microlensing surveys are carried out toward the galactic bulge, shown here, where the stellar density, and thus also the amount of light that is blended with the microlensing event, is high. These difficulties can largely be circumvented by simply waiting for the lens and source to separate, so that they can be resolved, allowing the flux of the lens to be measured directly. In this paper, we present a catalog of microlensing events from 2004 through 2013 that have high relative lens-source proper motions. These events either have already or will soon separate sufficiently to be resolved, facilitating direct lens flux measurements. The relative lens source proper motion is given in equation 1, where theta star is the angular source size, rho is the source size normalized to the Einstein ring, and Te is the Einstein crossing time. In order to select our catalog, we establish the following criteria. First, the event must display significant finite source effects. This allows us to measure rho from the microlensing model. Second, there must be multiband photometric data for the event. It is from color data that we are able to measure theta star. Third, the light curve must exhibit precise and dense coverage for robust determination of rho and Te. Finally, the event must have a proper motion greater than 8 milliarc seconds per year, which means that it will take 12 or fewer years from the time of the event for the lens and source to have an angular separation that is easily resolved with ground-based adaptive optics systems or space telescopes. In total, we find 20 events from 2004 through 2013 that meet the above criteria, 14 of which have extant analyses in the literature, and 6 of which we newly analyze in this paper. Figure 1 shows a CMD of the 6 events with new analyses. In each panel, the green square denotes the position of the source, while the red circle marks the red giant clump, from which we obtained the de-reddened source color and magnitude. An example light curve for one of the new single lens events is shown in Figure 3. As we can see, the light curve exhibits a rounded top at the peak magnification that is characteristic of the large source size that gives rise to finite source effects. In Figure 7, we have the light curve for one of the new binary lens events. Here, there are 2 rounded peaks, which again are signatures of strong finite source effects. This event is particularly interesting because the combination of its short timescale, with an Einstein crossing time of only 12 days, and small mass ratio, with Q equal to 0.05, indicates that the lens companion is potentially a substellar object, such as a brown dwarf or even a giant planet. Finally, Figure 8 shows the caustic geometry for all 6 new events. The caustics are shown in the red curves, the source size is represented by the yellow circle, and the black line denotes the source trajectory. In all panels, the absolute lens sizes, shown in the blue circles, are arbitrary, but in the case of binary lens events, their relative sizes are scaled appropriately. In the case of the 2 single lens events in the second and third row, we see that rho, the source size, is larger than the impact parameter. In the case of the 4 binary lens events, rho is of order the size of the features of the caustics. There is a myriad of instruments, current and planned, on the ground and in space, that have or will have the resolution necessary to resolve the source from the lens for all 20 of the events presented here. One current example of such an instrument is the Gemini Multi-Conjugate Adaptive Optics System on the 8.1-meter Gemini South Telescope at Cerro Pachon in Chile, shown here during laser operations. To conclude, we present a catalog of 20 microlensing events over the past decade with sufficiently high proper motions to resolve the lens from the source currently or in the near future with present and planned ground-based adaptive optics or space telescopes. These events provide an excellent opportunity to directly measure the flux and thus derive the mass of the lenses, which are typically objects that are difficult to probe with other techniques. Thank you very much for listening, and have a great day.